So today we will be talking about the time complexity of an algorithm which we write to solve a particular problem. Although here I have written time complexity, but generally it is the complexity analysis of a particular algorithm or a data structure, right? And I'll be explaining how time complexity is different from complexity analysis, but for the for some time let us treat it as time complexity. So before going into the details of the time complexity, we need to understand what an algorithm is. So if you think about an algorithm, you may come up with an idea that it should contain finite set of or finite sequence of instructions. Okay, then each instruction in the algorithm should have a clear meaning, and each instruction should require finite amount of effort to be solved by the computer or the processor, and each instruction should require the finite amount of time. So the effort and time are sort of different things, but again there are certain ambiguities. For example, finite amount of time can be 1 minute, 1 second, 1 hour, 100 days, 100 years, that can be. And again, when we say that each instruction should have clear meaning, then again this is also subjective. For example, what may be clear to me may not be clear to someone else, or the other way around, what may be clear to somebody else may not be clear to me. So everybody has different understanding of stuff based upon their background. So this clarity is also subjective, and finite amount will of course vary from a task which is being executed on a supercomputer versus Pentium 4, which are obsolete these days. So we need to have a comprehensive definition of an algorithm before moving forward. So the definition of an algorithm is that it is a finite set of statements that guarantees an optimal solution in finite interval of time, right? So here three words are very important, and they have been underlined here as well. First of all, finite set of statements. So in your algorithm or in your solution, there should not be some such statement or some certain block which may take your algorithm to an infinite loop. At times this happens. For example, if you if I write a loop for I is equal to 0 and I is this is now the condition, right? So, and I say I is greater than, let's say, -1, and now I say I plus plus. Now obviously this particular piece of code, if you see here, I will be 0 and then it will be incremented to, let's say, 1, 2 and so on. So it will always be greater than -1. So this piece of code is going to be executed forever unless until the electricity shutdown may not terminate it. So this is again, if your code contains such portion or any other portion which takes it into an infinite loop or infinitely makes it execute infinitely, so that will not be an algorithm, right? Secondly, your algorithm should guarantee the solution, right? For example, if you have written a solution which is maybe if I give you an assignment and you execute it on your own computer and you say that okay, my computer has Core i7 processor and I open that particular assignment on my own computer, and for example my computer is Core i3, and it does not execute on my computer, it means it is not guaranteeing the solution. Or otherwise, if you say, okay, my operating system is Windows, right, and I run your solution on, let's say, Mac operating system, and it does not work, so it means it does not guarantee the solution. Again, remember, I am talking about an algorithm. An algorithm is a set of statements to solve a problem. I'm not at present we are not concerned about any particular language, C, C++, Java, Pascal. No, an algorithm can be written in any language, right? So the important thing about an algorithm, there are three important things. First is that it should have finite set of statements. Secondly, it should guarantee the solution, and by guarantee we mean that when you run that algorithm on 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 a Pentium 4, it should work on Pentium 2, it should work on Core i7. If you have executed a program, run a program on Mac operating system, that algorithm should also work on Windows operating system, maybe Android operating system. And if you have written the algorithm which works on Earth, it should work on Moon as well, right? Now this is a different example, but actually this is a very relevant example. Okay, let me try to draw a moon here. I have made a small sized moon so that we can distinguish between Earth and Moon, right? And now why have I given you example? For example, if you program something for a space shuttle to open its door, right, and you say, okay, I've debugged it and I've seen that it is working perfectly fine on Earth, and if somebody goes on Moon and then there he or she keeps on pressing the button and the door does not open, and then you give us a signal from the Earth that, oh sorry, I made it for Earth only, it won't work on Moon. So it means whatever piece of code you have written for this particular scenario, that is not an algorithm. You may call it whatever name you like, but it won't be an algorithm. An algorithm must have these three properties. It should have finite set of statements, and it should guarantee a solution. And finally, the most one of the important aspect, it should guarantee an optimal solution, right? There are two different things. One is called optimum and one is called optimal. Okay, let me, sorry. And here it is optimal, right? This is optimal and other one is optimum. Optimum, right? For example, let me give you an example to distinguish between optimal and optimum. For example, if there is a class having a couple of students, okay, let me make their faces right. Okay, this takes time as well. These are students in a class, and this student has CGPA of 2.7, this has 3.1, he has a CGPA of 2.1, and he has a CGPA of 3.9, right? Now if we see here, the highest among these four students, the highest GPA is 3.9, so this is the optimum, right? However, the total CGPA was 4, so this 4 is the optimal, right? So optimum is a value which is the best available value across across a search space. Here the search space is these four students, so among them the highest possible value which we could have obtained, which they have achieved, is 3.9, but the perfect value was 4, so that is the optimal value, right? Now coming back to algorithms, in algorithms, if there is an algorithm which says 3 plus 3 is equal to okay 5.9, okay, and another algorithm says okay 3 plus 3 is equal to 5.99, and other algorithm says that 3 plus 3 is equal to 6. Okay, now this is not an algorithm because it does not give you the optimal solution, we may say that okay, this is nearer to 6, but it is not giving you an optimal solution. That is why it is not an algorithm. This is not an algorithm as well, but this one gives you the optimal solution. So this is the algorithm, right? So in total we have to define algorithm, we always have a finite set of statements that guarantees an optimal solution in a finite interval of time. So these 3 points must be kept in mind. If even a single point among these 3 is missing in a piece of algorithm, you cannot call it an algorithm. You may call it chair, desk, or board, or football, or whatever you like, but it won't be categorized as an algorithm. Right. Now, and let's assume that if we have multiple algorithms, now which one will be better? For example, if we talk about sorting a list of numbers or a set of names, for example, then there are a number of algorithms which are available. All of them have finite set of statements. All of them guarantee an optimal solution, right? So all of them are algorithms. For example, to name a few algorithms, we have bubble sort, that is an algorithm. We have quick sort, that does sorting as well. We have merge sort, and there are a whole lot of sorting algorithms. Now, how do we compare two algorithms? That which one is better and which one is sort of, let's say, slow or whatever. So there are two basic criteria for that. The first one is that it runs in less time, and the second one is that it requires or it consumes less memory. But among these two, if we have to opt for, think about which one will be better, which one may be rather more important. Yes, you are right. We will go for the one which takes less time, because you can purchase memory. For example, if you want to increase RAM for your computer system or any other system, you can go to the market, you can purchase extra RAM, you can spend money, and you can upgrade your system, right? But you cannot purchase time. For example, if you did something yesterday and you want to go back and want to fix it, however, you cannot do that irrespective of the amount of money or resources you have. You cannot go back in time. So time, as compared to memory, time is more critical here. But having said this thing, that there may be problems where we may be more interested in saving memory than time. This totally depends upon the requirements of the problem domain or your customer for which you are making a solution. But generally, we are always interested in addressing the time constraint or making sure that our algorithm is more efficient in time, right? Now, the efficiency of an algorithm is actually a measure of the amount of resources it consumes in solving a problem of size n. And when we say that an algorithm consumes resources, the two main resources it consumes is one, as I mentioned earlier, is the time. One is the time, and the second one is the memory space. These two things it consumes. So, and it is actually, when I say that the efficiency of algorithm is a measure of the amount of resources consumed in solving a problem of size n. So, for example, if we draw here a graph, and now, for example, this is time, for example, it says 1 second, this 2, 3, 4, 5, 6, and let's say this is 7, right? And our input size, for example, we are sorting an array of n elements. For example, if the array has one element, now the array has two elements, the array has three elements, the array has four elements, 6, 7, 8, and this is again a hypothetical example. Now, for example, for 1 second the algorithm takes for an array of one element it takes 1 second. For an array of two elements it takes 2 seconds. For an array of three elements it takes 3 seconds, so on and so forth. So now this is the behavior or pattern in which this particular algorithm works. But again there may be another algorithm that may behave like this. Now if you see here, at this point it is for a problem size of 4 it is consuming 6 seconds, but this blue line for the problem size of 4 it is, okay, let me make it blue, it is consuming, okay, some 4.5 seconds, right? So this is how we measure the efficiency. I will be explaining this thing in further detail, and then you will be able to understand it in a better way. So wait for that. But again, generally speaking, the two resources which are eaten by an algorithm, which are consumed by an algorithm, which are required by an algorithm are time and space. Now it would seem that the most obvious way to measure the efficiency of an algorithm is to run it and measure how much processing time it needs, right? Now for example, we have some student has written an algorithm and he has written this blue algorithm, right, to solve a problem, for example to find the largest number in a linked list, for example, okay? And then there is another student who has written this green algorithm on a piece of paper. They have written this again is written on a piece of paper, and other student has written a red algorithm on a piece of paper, right? All of them does what? They find the largest number in a linked list, right? Now one way to find the how much time or how much efficient an algorithm among these three algorithms is to, okay, we will code all of these three algorithms in a compiler in C++, Java, Pascal, whatever language we like, and then we will execute them, and we will note that how much seconds or minutes or hours or microseconds, nanoseconds they consume, right? So apparently this is the solution, right? But actually it is not. For example, if all of those three algorithms were algorithms, they were all finite set of statements, they guaranteed an optimal solution. So and then you have coded them all. So if one algorithm is, let's say, marginally better than other, right? So what's the point in measuring their efficiency? If you have coded one, go with one, right? So the complexity analysis basically deals with the analysis of algorithms without even programming them. Before programming them, you see the face of the algorithm, you see certain a line of codes in the algorithm, and then you analyze that, okay, this will take this much time. So that is what we deal with while analyzing the algorithms. Now the factors the factors which can influence the processing time of an algorithm, there are many factors, but one of them is operating system. For example, one of them is the hardware. For example, you are executing your program on Core 2Do machine or Core i7 processor. So there will be a lot of performance difference due to hardware. And then operating system as well. There are certain operating systems, like for example Microsoft Windows, which are GUI, graphical user interface based operating systems, and there are certain operating systems, for example DOS, disk operating system, and that is a text based operating system, and there are other operating systems as well, and they have their own performance issues. So the execution of the algorithm is also influenced by the type of operating system installed on the machine. Then the compiler which you use, there are certain compilers which are slow, there are certain compilers which are quick, right. So that also influence the execution time of an algorithm once it is coded. And then the size of the input is obvious factor. For example, again giving you an example of sorting. So if you sort an array of 10 elements versus sorting an array of 10 million elements, there will be a difference. And then nature of the input is also important. For example, if you sort only numbers, for example 1, 2, 3, 99, so that is something different. But if you sort alphabets or names, for example Zia, Ali and Bilal, right. So the nature of the input also influence the execution time of an algorithm. Here if you see here we have 1, 2, 3 and 4 values, and here let us say we also have 4 values, but these 4 values are alphabetical, they are names, they will be treated as 2D array, each single element. So this input is going to take longer as compared to this input. So this also influences the execution time of an algorithm. And then the algorithm itself, for example, how many loops have you used in your code? How many if then else statements have you used? Have you used if else statements or if statements, right? So for example, if your code uses if, right, and then it uses if again, and then it uses if again, right, versus your code uses if and it says else if, and it again uses else if, right. Oh, sorry. Now this red piece of code is going to take long, because if you check a condition and this condition is true, but the compiler will check this condition and this condition as well. But here if the first condition is true, it is not going to check this one, it is not going to check this one, right. So this one will be quicker than this one. Again I will be telling you about these techniques later, but algorithm is a major factor here to address. Now if we want to improve the performance of the of our code, which of these 6 factors should be addressed to make sure our algorithm or our solution is working quickly or efficiently? Think about it. Of course, maybe the easiest one would be hardware. Simply replace the computer and in the new computer it will be working fine. But as a computer scientist, our focus will be to write efficient algorithms, right? Our focus will be the algorithms. Now the running time of algorithm. Now the running time of the algorithm basically depends on majorly 2 things. One is the size of the input and the other one is the nature of the input. As I mentioned earlier, that whether the input is numeric, alphanumeric, or it is a set of strings, right. So the execution of your algorithm, running time rather of your algorithm depends upon these 2 factors. So generally time grows with size of input. So running time of algorithm is usually measured as function of the input size. As I drew a graph earlier, let me draw it again. If you see, this is size and this is time. So for a particular algorithm, your algorithm may behave like this, right. So this line, I should have used different color. This line will basically show the general growth of the of your algorithm as the size of the input increases, right? So the running time is measured in terms of number of steps. Right, okay. Okay, the example is coming up, so let's wait for that. So otherwise the running time is actually executed in terms of number of steps which are operated or operations which are performed in an algorithm. And this number of operations, the time they consume is independent of any machine or an operating system. For example, addition operation may perform differently on a particular processor as compared to another processor. So we are not here when we analyze an algorithm, we only assume that okay, this addition operation will consume 1 unit of time, and we do not say that this 1 unit of time is equivalent to 1 second or 2 seconds or 10 seconds. No, we only assume that it consumes 1 unit of time, where this unit of time may be 1 hour, 1 second, 1 minute, because we want to ignore a lot of machine level or a lot of other dependencies. Now these are a few examples of preemptive operations that can be performed in an algorithm. For example, subtraction, addition, multiplication, logical operation, accessing an element of an array, input output for that matter. So now let us consider this particular example. If you see here, here we have a piece of code, right? So our first task will be to find the number of preemptive steps which are being performed here, right? So if you see here, now this assignment is one operation, right? If you see here in the for loop, this assignment is another operation. This is a logical operation of less than. This is increment operation. Now we call this statement 1, we call this statement 2, this is statement or operation 3, this is operation 4, operation 5 is assignment operation 6 is addition operation, this operation number 7 is accessing an element of the array, and this operation is the return operation, right? So in total there are 8 operations or functions or preemptive statements, primitive statements in the code. Now if you see here, this operation number 1, this one, this operation number 2, and this operation number 8, they are all being executed once, right? So they will be executed only once. And then if you see operation number 3, 4, 5, 6 and 7, okay, these operations will be executed for I is equal to 0, I is less than 10. It means they will be executed n times, right? So if we see here, there are 3 statements. There are 3 statements which are executed once, plus there are 5 statements which are executed n times, right? Now we can make this a simple function for f of n, right? This will be a function where n will be actually the size of the input. Now if we say that n is equal to, let's say, 5, so the output of this function will be 28. 5 into 5, 25, 6, 7, 8, 28, right? But if we say that n is equal to, let's say, 2, then this the output of this function for, okay, f of 5 is equal to 28 and f of 2 is equal to 13, right? So it shows that when the size of the input is 5, this piece of code is going to run or going to take 28 units of time. I am not saying 28 seconds, I am not saying minutes, or I am saying 28 unit of times. And if n is equal to 2 और ये 2 लग नहीं रहा, if n is equal to 2, then this piece of code is going to take 13 units of time. And for this unit of time can vary from the machine to machine. So here we are sort of generic, right? So this is how you analyze your piece of code, so that you can see that what is the performance of your code when it is executed. So this is enough for today's lecture, but I'll be explaining this thing in further detail, that how we will be drawing these graphs and how we'll be making a single numeric form or a single number which will represent the performance of such algorithm. But for today, you should know that how we extract number of statements, and then we analyze that which statements are being repeated for how many time, and how we actually resolve those. So if you see this code, we in this piece of code, statement 1, 2 and 8 are executed only once, and 3, 4, 5, 6 and 7 are executed n times because they are a loop. So this is a function, this becomes 5n plus 3. I wrote 3 plus 5n, which is the same thing. So 5n plus 3, and this will become a function f of n, which is equal to 5n plus 3. Now in the next lecture I will be explaining the growth of the algorithm, but this should be sufficient for this week. Thank you.